Alrighty, so here's our examples for 9-1. What are the coordinates of the vertex of each graph, minimum or maximum? So here we're not using the formula yet. We're just kind of looking and seeing where it's at. We'll get to the formula part again as practice here in a little bit. So obviously if it's upside down like this, right, having that negative a, it's a maximum. You can read right here, it's 0, 3. It's graphed nicely. B, again, it opens up here. A is greater than 1, greater than 0, I'm sorry. That means that this is going to open upward. So it has a minimum, and the minimum is 1, -1. We can see that right here. What is the vertex of this one? Is it minimum or maximum? Obviously, again, opening up. So it's a minimum. And in this case, we can see that is -2, -3. I don't know why there's double negatives on that. That's kind of weird, but -2, -3 has a minimum. So a little practice in graphing here. Again, graphing the form y equals ax squared. Don't have a b or c on this one. Those are both zeros. Graph function y equals 1/3 x squared. Make a table of values. That's currently what we're going to do here, making a table of values. We have a 0 for x. Obviously, going to create, up here, putting a 0. 0 for x makes the number 0. 0 times 0 is 0. 0 times anything, again, is going to be whatever that a is. In this case, 1/3 is 0, so 0, 0. And I do expect by now that you're able to do the math on this pretty easily. Plugging in a 3, so that's 1/3 times 3 squared, so that's 9 times 1/3, which is 3, so 3, 3. And 6, so 6 squared is 36, a third of that is 12, so 6, 12. Now here's the great thing. This one reflects across, so its line of symmetry here is the y-axis. So it's easy just to go ahead and flip those points on both sides. Right, so I graph that 0, 0, that's the minimum. Graph my 3, 3. I'm also going to graph -3, 3, right? That's symmetry piece. I graph my 6, 12. Also going to graph -6, 12. Again, that only works when the axis of symmetry is the y-axis. Let me say that again. This trick only works when the y-axis is the line of symmetry. Otherwise, you could literally just reflect it across, right? So you graph your 3, 3, and you go, okay, well, that's 3 over. We'll go 3 more the other way. The 6, 12 is 6 over. Go 6 the other way across that axis. That way, no matter what the axis is, you can do that. Again, here I do expect, again, that your math is good. I've started the problem off though for you. Graph the function y equals -3x squared. What are the domain and range? So, obviously, plugging in a 0, right? I'm going to get 0, 0. Again, we're plugging into here. And I'm skipping over doing the actual math here because we spent a lot of time on this, on exponents, so I expect that you can do this. Plug in a 1. We're going to get -3. I plug in, oops, hang on a sec. Plug in 1, again, we're going to get -3. Plug in -1, we're going to get that -3. Plug in 2, get -12, and plug in -2, get -12. And again, graphing those. We know in this case, when there's nothing else, when B and C are 0, that the y-axis is going to be our line of symmetry. So we just graph straight across, plug in that, plot that 0, 0, 1, -3. And again, you say, look at that's 3 over, or 1 over rather, so I'm going to go 1 the other way. Same thing with the 2, 12. 2, 12. And again, that's 2 over, so I go 2 the other way. And just continue like that to graph it, and you create a nice gradual curve when we do it. It's not a V, right, or an upside down V. A nice gradual curve that goes through the points, which does get steeper, obviously, as you continue to put in larger and larger numbers. A little bit here about comparing the widths of parabolas. So part of this is understanding that whole parent function, the y equals x squared thing, and how changing each of these makes a difference. So y equals -4x squared, so the -4 flips it upside down and makes it steeper. Right? Or how do you want to put that? Shallower? I don't know what the term is there. So in other words, Not flat like this, but more like this. Does that make sense? Hope so. And then continuing with that, notice that when I put a fraction in there, it makes it more, makes it flatter. Maybe that's a better term. And then back to the parent function, or f of x rather equals x squared. Everything's compared to that. So again, if a is a fraction, so smaller than between 0 and 1, it gets flatter. If it's a larger number, so the absolute value of that a is larger than 1, it gets steeper, for lack of a better term. So on the got it's, that'll be on the next slide here. And I went ahead and used my Desmos here to graph those for you. So widest to narrowest here, just so you can see them. Obviously, this is the standard, right? This is the apparent function flipped upside down, and as you can see that here in blue, right? And then when I apply that 3, in this case, notice how it becomes even narrower, or steeper, however you want to put it, compared to the blue one. And then when I apply a fraction, right, it flattens out some. So that's an important thing to understand. And again, obviously, the negative flips it upside down, right? Positive keeps it upright. So in order, obviously, from widest to narrowest, so the widest one, I guess that's a term I was looking for, right? Wide to narrow. The widest one is the negative 1/3, because that fraction piece. And think about doing negative 1, or think about doing 1/10. Going to make it even wider. There's the parent, right, or the flipped upside down parent function. And then, again, that 3 makes it even narrower. Okay, so we're going to go ahead and add the c on, no b this time, so no bx, and find out what that's adding that c on does to it. So again, this is important. Back to the idea of that parent function. If you have the parent function, the y equals x squared, being like this, we find that adding the c on forces us to move up, or if we subtract, go down. We'll talk about the b later. The b will cost us shift in left to right. And we will spend a day playing with this with Desmos in class as well. So let's talk about this one here. Graphing y equals ax squared plus the c. So we have 2x squared plus 3. How is that different from 2x squared? So obviously, first off, 2x squared is going to be narrower than just y equals x. And when I add that plus 3 on, it literally shifts it straight up 3. And you can see all the points here I graph, plugging negative 2, negative 1, 0, 1, and 2. You can see versus 2x squared, and then the plus 3. It's literally adds 3, bumps it up by 3 at every point. And the expectation is that when we're done with this, you know that. You understand that moving it up, down, left, right, what causes that to occur. Now, again, I'm obviously not testing. There'll be a quiz, but I'm not testing over that part. But you'll find it unbelievably useful as we continue our study of these quadratics. So here, back to that idea of graphing here the parent function, y equals x squared. And again, I trust that you can plug in the points and figure out, what each of those are. 0, 0, right? 1, 1. In this case, 2, 4. Negative 2, 4, right? So on and so forth. 3, 9, negative 3, 9. I trust that you're able to do that. And subtracting that 3 subtracting the 3 from that slides the whole thing down exactly 3. So it grabs it and slides it down. That's the only difference it makes. So that 0, 0 becomes 0, negative 3, right? That 1, 1 becomes 1, negative 2. So when I say sliding down, I mean sliding down the y-axis, right? Hopefully we understand that piece when it comes to graphing. So understanding what this does to the parent function itself. Now I know you're excited because obviously I'm going to turn this into story problem fun, right? Yeah, I know you're excited. Go and cheer. It's okay. So using the falling object model, kind of fun. Nature, an acorn drops from a tree branch 20 feet above the ground. The function h equals negative 16 t squared plus 20 gives the height h of the acorn in feet after t seconds. So again, height, seconds. What is the graph of this quadratic function? At about what time does the acorn hit the ground? So we're looking for that 20 feet, like how long it takes it to drop 20 feet. So something to talk about, though, before we do this. You got to think to yourself, can we have a negative t here? No, doesn't make any sense. Not even if you had a time machine does it make sense. It's just going to go back up to where it was on the tree, so kind of pointless there. So thinking about what that means. And our h, right, are we going to end up with a negative h? What does that mean? So the function for the acorn's height, given right here, plugging in our 0, 0.5, 1, and 1.5. The function's graph at the time the acorn hits the ground, so graphing right here until boom, right, until our y is 0. Obviously happens somewhere in here, because can you have negative? I mean, unless that thing slams to the ground, your height is not going to be negative. That's down here somewhere. So graph the function using the first 3 ordered pairs. Do not plot this one again because the height is not negative. So neither time nor height in this case can be negative. So we plot our 0, 20, our 0.5, right, our 0.5, 16, our 1, 4, and then boom, sometimes slightly after that 1, between that and 1.5 seconds, it hits the ground. Doesn't go any farther. Again, it's not being fired into the ground. It's going to hit the ground 0. Okay, so similar problem. By the way, I want to make sure we understand that the graph is not the path, right, that the acorn falls. It's just notice how it starts falling, and then it starts falling faster, right? And then we have that distance hitting there. So as it hits time, rather, it gets closer and closer to the ground quicker. Maybe that's one way to think about it, instead of a straight line acceleration. So anyway, again, this is not the path, right, that it falls. It's not chucked out from the tree. And remembering that height can't be negative. Time certainly can't be negative. But a slightly different equation this time. So what's the graph of this function? At about what time does the acorn hit the ground? So again, notice we're at about one time. We're not worried too much here at this point in getting the exact, the exact time. So again, plugging in your points here. Looking at the original, instead we're going to be at plus 60, right? Or plus 70, I'm sorry. So it's going to alter each of these just slightly. And what they'll look like then, let's give a table here. So I went ahead and calculated the table of values here. And again, if you need help with that, please do see me. It's something I expect that you are able to do by now, but again, I'll sit down with you if you're having some trouble making some errors or whatever. But anyway, so 0 squared, right, times negative 16 plus the 70 is 70. Notice each of these compared to these values, it's literally 50 more because the other one was plus 20, right? This is plus 70, so it's literally 50 more at each turn. So where does it hit the ground? Well, if we go ahead and graph it, somewhere around 2-ish, right? Because we're going to have 2. It's somewhere around 2, I should say. It's at 2 it's still at 6, but just past the 2, right? So notice here, 2, 6 is about right there. Just past the 2, it's going to hit 0 because we know at 2.5 seconds it's at negative 30, so it's down here. And again, which doesn't happen. It doesn't go drilling into the ground, is the idea. So somewhere around a little after 2 seconds, we'll say. Part B of this, what are a reasonable domain and range for the original function? So again, domain, range, right? What kind of things we're going to put in? Well, the domain, 0 to about 1.2 seconds, right? If we think back to the graph of this one, 'cause it's just after 1 second. And then that range piece, again, is obviously going to be between 0 and 20 feet. Just like for this one, it's going to be between 0 and 70 feet because it's not going to drill into the ground.